the next one is a little bit special. So this is just to cover the case that the integram is not an even function. But this is obviously not a general case of x cubed. But sometimes when you're lucky, get a form that you can use some tricks because it's one of these situations. So previously we consider the x squared, right? X squared. Then we argue that you can use the fact that this is an even function. You can change that to to minus infinity to infinity divided by 1/2. But not for this case. We cannot go to negative x because I mean it's not an even function, and consider the negative part also is troubling because that can be singular. The denominator can be 0 at -1, obviously. The x is -1, the denominator is 0, so you cannot go to negative x. All right, but it has only one single power x, so that give you a suggestion that you don't actually need to refract to the negative root axis. You can find another line from 0. So you have the complex thing is so the circumference is not the singularity. So the integration is from 0 to positive root axis x, right? And now if you find another line that can we translate x translate c cubed. So when you extend it to complex bit, it becomes c cubed plus 1, and back to c cubed plus 1. Just c cubed is fine, so because 1 is just a constant. C cubed tends to some kind of r cubed also, right? And the possibility is that you have say that this becomes c cubed. C is r e to the I theta, right? And EQ is r cubed e to the I g theta, right? So in order that it becomes just r cubed, then this becomes 1. The exponential function becomes 1. It means c theta is integer multiples of 2 pi. So the first one you have is 2 pi over 3. The theta is 2 pi over 3. And 3 theta is just 2 pi. E to I 2 pi is just 1. So get back to r cubed. So that the integram will be the same as that one. So we don't need to refract all the way to the negative root axis. We kind of refract to another line. So this line is this is equals to r cubed for theta is 2 pi over 3. Right? In that case, 2 pi over 3 is just separate in the 3 parts. Just one trying to this one, right? This is 2 pi over 3. Right, and also the integram has poles and has 3 poles. The 3 poles is x cubed plus 1 equals to 0, right? And we already talked about it. -1 is a pole, and then the other pole is also the solution x cubed equals to -1, or x equals to -1 to the 1/3 power. And if you remember your complex number classes, you know that that kind of solution is just separate, divided the 2 pi by equal number. Now it's 1/3 power, so divided by 3. So this is a pole, so the other pole would be on the same circle, which is a unit circle for this case. separate the angle into equal parts. So it's 120 degrees, 120 degrees, and obviously this line will be pi over 3. This is also pi over 3. Right? So there are three poles altogether, -1, and then the other two poles at e to the. So these two poles are these two poles e to the plus or minus. Right? Is that okay? So you get the location of the pole, and these are all simple poles. Any questions? Okay. And now you figure out the the poles. Now the contour, you want to find a closed contour that enclose at least one of the pole. So now, and then you know that along this line, the integram, at least for the denominator, is the same as the along the real axis. So there's some kind of refraction. So you want to close it, connect this one, and another one. And we use the fact that we can close it along a large circle, and the integram will be 0 because you have a 1 over x cubed power for large value of z, 1 over z cubed power. So you can close anyway. You can close this way or close the other way. And close this way is simpler because you only have one pole, right? So close this way. This is for large R. I'm not sure it's very good. This is for R goes to infinity. And now this loop will have the original one, which is we call I just this one. So 0 to infinity along the real axis, and then go to the large arc. It's not semicircle. This is 2 pi over 3, one third over 2 pi section, and then go back, right? This is let's call it I. Okay. So we just write symbolically I plus C infinity plus I1 is 2 pi L times the residue at this one. This will be e to the 1 pi. Okay. All right. So that's set up the residue theorem, right? And now the C infinity, we already argued that because of the integram is going to 0. I is what we want. Now we only need to get I sub 1. I sub 1. I sub 1 is along the line. This line is C. This line is C equals to all e to the I 2 pi plus 3, right? So, and then it's from all. So dz is dr times the same phase vector, right? First you change obviously change everything to dz. So dz becomes r dr and then c cube we already argued that c cube is just r cubed. And r, now r is from close the loop this way, so the direction this way. So r is for infinity to 0, right? So this is when you compare this with that, you know that this is minus e to pi e times I, right? So now I plus I plus I sub 1 is 1 minus e to the I 2 pi over 3 times I. The right hand side, at the left hand side is this. The right hand side is the residue, so 1 minus copy it. I 3 pi c I equals to 2 pi I residue. Now the residue is you need to multiply by so this separate into 3 roots, right? And then you multiply z minus this root, which is c minus. This is the graph is too complicated. Yeah, right somewhere. Yeah, this pole is z equals to e to the minus c, right? And then the c minus this one to cancel, and then the other two roots are c minus one of which is c plus one, and then z minus this one, or this one, which is e to the minus I pi, which is the, and then z is take the limit of e I pi over 3. So e I pi over 3.
This one require a cube, the x cube term.
This one?
Yeah. The cube term is not required when we are
X cube term is
yeah,
not required.
There is a cube and there is a power of cube, so will it be for I pi?
I pi? Where is I?
Because of the cube. No. E exponential of I pi because of the cube. It's x cube.
No. I factor it. So I can't probably going too fast. So CQ minus 1 equals to E plus 1, right? Z minus E to the I pi over 3. E minus E to the minus I pi. Right? So this is plus 1. This CQ plus 1 equals, right? Just writing down the 3 would factorize this into 3 roots. Okay, and then substitute in here. For the simple pole, in the residue you calculate from this pole, you multiply by this factor, right, to cancel this factor, and then evaluate z equals to this root, and then evaluate these two factors, this times that, and z evaluate here. Okay, do you know what I'm doing? Okay, so my method might not be the best way. Maybe the other method that's better. Right. Then I mean now you the rest is simplification. Let's see. It's just compact manipulation, and just need to be a little careful. Get everything. Okay, so first, obviously, there's this one. It's like a sine function, right? Sine pi over 3 divided by 2i, so 1 over 2 I equals to you have a pi and divided this one and the 2 will combine to sine pi over 3. All right, it's getting there. And now we need to divide this factor to this side. Let me see. So you have this factor plus into the I this here, and then 1 minus e to the I 2 pi plus e. Okay, hopefully that will work. All right. And we just need to multiply together. 1 times 1 is 1. And then you have this times that is e to the pi, right? E to the pi is I pi. E to I pi is minus 1. And then you have but wait a minute, the best. E to the I pi plus 3 minus e to the pi 2 pi plus 3. Right. So and this is minus 1, so that's effective. This is just 2. And this 2, I mean, it looks horrible. I mean, you can write it as the cosine part and sine part, or you can do it graphically. So this is basically, this is along the line I pi over 3. This is along 2 pi over 3. So there's so this value is this value. And this minus that, they have the same imaginary part. And then the real part just refracts. So you have 2 of the real part. So basically 2 of cosine pi over 3. Right? So 3, this is 2, that's 2 of cosine. And what is that? Let's see. Right. Do we get it? Do we get the correct answer? Is it the correct answer? Right. I mean, this algebra. You have now we need to figure out what pi over 3 is 60 degrees, right? Figure out 60. Is it true? So, this is pi over 3, right? So cosine pi over 3 is 1/2, right? 1/2. So this is 1/2 pi times 1 plus 3. 1 plus 3. So pi over 3. Pi over 3. Is it? Yeah. Pi over 3 is, yeah. I mean, there's further simplification. You substitute sine pi over 3 is square root of 3 divided by 2. Square root of 3 divided by 2. 2 pi over 3. Okay. Well, I mean, the first part is straightforward. The second part is just tedious. The evaluate. Right? Where, where are you pointing? This one? Why is it 0? This is integrating this integram along the path that when z goes to infinity, along this path is along z equals to r e to the theta, and we let r goes to infinity, right? And the integram has r cubed here, right? So you have r divided by r cubed is 1 over r squared, right? And then the I mean you have another r, the r, right? This is r, and then e to the I theta times I. If you write it explicitly, like we where is one of those e's? This one, yeah, this one is here. This one is this path. So the whole loop is going here and then going this loop, going back. this slope is zero. I mean, I should say, if you want the notation, that is I. This is the path is C infinity. The integral is I along C infinity. So that is zero. So this is this one, which is this path, right? And then you integrate along this path C infinity, which is R goes to infinity, going from theta from 0 to pi over 3. Along this path, this integral is 0. And then you press this path from infinity to back to 0. It's I sub 1. So this path is 0. The integral along this path is 0 because the integral is going the 0 faster than 1 over r. That is what we argue in the other case. When you integrate, you don't have the exponential factor. You require the integral go to 0 at large infinity faster than 1 over r, or 1 over the distance, right? And so this is r cubed and obviously greater than 1, faster than 1 over r. And that will make the integral along the large arc to be 0. So, okay, so that is basically the case that we talked about. Before we talked about exponential, and that is the argument.